Welcome to the STEM Pathways podcast, where we delve into the fascinating world of science, technology, engineering, and math. I'm your host, Rohan Sharma, a passionate explorer of all things STEM. Each episode, we bring you captivating stories, cutting-edge research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we unlock the mysteries of the universe and explore the endless possibilities of STEM. Let's get started. Today I'll be interviewing David Attwood, who holds a Ph.D. from NYU and has been a professor at UC Berkeley since 1989. How are you doing today?
Very good.
Yeah, thank you for joining me on the podcast. So to start off, I wanted to ask what made you choose your major for your bachelor's?
Yeah, so I enjoyed math very much, and I also enjoyed high school physics. It was really great. And I wasn't very well informed about what my options were. It wasn't something my family was into, or even I was into. The fact that of going to college actually wasn't high on my list. I didn't take the SAT, for instance, and then fortunately, the guidance counselor at the high school called my mother and said, "Hey, your son should really take this." So we did. I applied to one school. They took me, although uh, my high school record wasn't terrific. But they were starting a new engineering science program. I was not aware that you could actually be a physics major, which if I had known, I would have probably chosen that. But at any rate, the engineering science program at this little university, actually college at the time, Hofstra College, was just a terrific program. And it introduced you to a lot of different aspects of engineering and physics and lots of math. So it was a great starting point.
Yeah. And then, what made you want to move on and do a PhD?
Well, I got really interested in what's called plasma physics. As an undergraduate, I really enjoyed electromagnetic radiation at all wavelengths, and I also enjoyed fluid mechanics. And it was in the library and needed a break, and I just took a walk around the stacks, and I happened to find a bunch of books, one area of the library that had the equation, Maxwell's equations for the electromagnetic radiation and all the fluid equations in one book, and it was called Plasma Physics. And I said, "This is for me. I want to learn more." That's how I got interested and decided I should go to graduate school. Um, so that was the launch.
Yeah, so what was your experience like while getting your PhD, and what was your research about?
So it was about plasma physics, and I had a fantastic faculty advisor who was a great mentor, and we continued to be in contact for many years. As, by the way, was my undergraduate um, um, ch chairman of engineering science, the guy who started it. He and I remained in contact for decades later. We always knew how to contact each other. And in fact, one of the points I was going to make to anyone who might be watching it, anyone, is how helpful it is to have a mentor. It's worth searching out and making contact with someone who's going to give you guidance and also speak up for you when opportunities appear. But anyway, so I went to graduate school in plasma physics. I was thinking I would work on fusion, probably magnetic fusion, but just as I was graduating, this new topic appeared called laser fusion. And I joined that, and it was really terrific. You got to use high-powered lasers. It had some nuclear physics in it, fusion reactions, and lots and lots of plasma physics and lots of instrumentation. And it fit me perfectly, and I just enjoyed it. I did it for 10 years, and I enjoyed every day of it.
Yeah. And what kind of jobs were you holding then?
I'm sorry?
Or what kind of jobs were you doing then? Can you talk a little more specifically about what you did day to day?
Oh, what I did. So there were no experts on laser fusion. It didn't exist before that. So what they did was they hired a large number of students who were rated pretty good by their faculty and were recent graduates. So there was a whole bunch of us, recent PhDs. No one had experience. I knew about plasmas, wanted to learn about lasers, and did. And I identified two projects that were really important. One was to understand the plasma surrounding the little microcapsules. They're about 100 microns in diameter, and they contain isotopes of deuterium was the idea, and they get hit by laser light. And how is the laser light absorbed by that capsule wasn't really known, but it was understood by many of us to be critical. How was the laser light absorbed? Was it some nice benign thermal process, or did it involve unusual things which no one had really looked into because the laser intensity was so high? So I decided I should measure what does that plasma look like around this little microsphere. So again, 100 microns, about the size of a human hair, little in diameter. And so I did that, and I was able to measure those plasma properties. I used something called holography. Ultraviolet was needed, holography. And the other topic I looked at was, well, in laser fusion, the laser light is absorbed in the outer regions of the sphere. The light's focused on it. They're short pulses, nanosecond at that time, longer now. And when the light is absorbed, it heats the outer surface, and the outer surface expands. And then, as we know from Newton's law, for every action, there's a reaction. So the expanding plasma going out drives some of the wall inwards, and it collapses, it converges around the gas and heats it when the incoming energy, the kinetic energy, is converted to thermal energy. You get a nuclear reaction. But there are lots of computer simulations, but nobody ever, and there were some images, just what you call, I guess, time-lapse photography, just a two-dimensional image, but nobody ever seen it in time. And the group I worked in made cameras that could record X-rays and were very fast. They had resolutions of so many picoseconds, maybe I think 15 picoseconds at the time. So I made up a pinhole imaging system for X-rays that would allow us to see by the X-ray emission, initially hot on the outside, later watching it go in, and then really lighting up in the center, and do that as a function of time. So I had space-time implosion characteristics of a fusion plasma. So those are my two projects, the most successful of the two.
Yeah. So when do you make the decision that you want to go ahead and be a professor?
Well, I had always thought through my PhD that I would like to be a professor. I was kind of thinking of a small school teaching physics, stuff like that. But although that was my plan, then I got involved in fusion and research, and I enjoyed that a lot. And so I was working at Lawrence Livermore National Lab at the time. That's where the laser fusion program um, was existed, and we were looking for fusion. Fusion has two parts to it. This may be more than you want to hear, but fusion, we were thinking fusion to produce energy, nuclear energy, for electricity, for houses and stuff like that. That's what I was interested in as an important environmental option. There was a similar program at Lawrence Livermore, or interest in using laser fusion to simulate nuclear weapons. That didn't interest me so much, but they were just sort of in parallel. And at a certain point when I was there, about 10 years, we came to understand that there was a difficulty with this high laser intensity right on the capsule, which was the method that would be used to produce electricity, was the idea. The absorption process was not benign. It created a lot of high energy particles, and to make it short, we came to understand that fusion for energy production, electricity, was not going to happen. It wasn't going to happen for 10 years or more. So I decided I would move on. Recently, there's been great progress, but on the other side of it, the whole round side, or the weapon side, has made really gigantic progress in the last year, but it's hardly related to producing electricity. At any rate, for me, that was a decision. It wasn't going to happen. We weren't going to be successful for a decade or several decades. So I started looking for something else to do with my knowledge about X-rays and also about holography and coherent radiation. And I learned that not too far away from me was Lawrence Berkeley National Lab just above the UC Berkeley campus, and they wanted to get they wanted to build a new X-ray facility, very big, size of a football field, would cost $100 million just to build the thing, more money to make use of the X-rays. And so several friends said to me that I should look into it, and they would speak to the director. They did. I interviewed, and they offered me a job, and I went there and I helped them to understand how they could use this, what's called synchrotron radiation or undulator radiation, how they could use that actually to get coherent X-rays. It required some filtering, what we call spatial filtering. And I brought that to them, and it played an important role in getting the facility funded. And so first uh, uh, um, I was the first scientific director because of those inputs about how to get the coherent properties. In fact, we had a terrific article in Science magazine in 1985, it was, and that helped to get the facility funded. And I remained active with that facility for a long time and still have some contact.
Yeah. And then while you're doing that, were you still a professor?
No, I wasn't a professor yet, but the UC Berkeley campus and Lawrence Berkeley National Lab are adjacent to each other, contiguous. And here it was, I was a newcomer, and I had brought these ideas of coherent X-rays, not X-ray lasers, but having much of the properties, desirable properties of X-ray lasers and how to use it, and also what kind of X-ray optics you would need. So we started a Center for X-ray Optics. We had the article I mentioned to you. It was a lead article in Science magazine, and at the same time, or almost the same time, we had another fellow and I, James Underwood, we published a lead article on X-ray optics and the opportunities it brought in the magazine Physics Today. So we had two important articles, and the chair of the physics department invited me to come and start lecturing in the physics department at UC Berkeley, which I did for several years. And at a certain point, a decision was made or recommended that actually this was more of applied physics, and it might be good to start a new PhD program in applied physics. And so I led an effort with many faculty members on the Berkeley campus. I invited them to join. And what started out as an idea of having an applied physics program got changed a bit. One of the members of the faculty was Y.T. Lee, Yuan Lee, um, and Yuan said, well, I'm not a physicist, I'm a scientist. Could we call it applied science instead of applied physics? And we'd be throwing a wider net. So I thought that was a great idea. It was a breakfast meeting. We changed it. Okay, we're going to be applied science. Other faculty members were from the College of Engineering, and they said, well, what about us? We're sort of engineers, not we are scientists, but maybe we could add and technology. So there is a PhD program on the UC Berkeley campus now called Applied Science and Technology. People can look it up on the web, and it's super successful, and its students win awards, get great publications. It's really turned out to be a very popular PhD program, and I'm still very much associated with it. I was on the campus yesterday for a meeting. So I came for LBL for a big X-ray facility, but wound up teaching and creating a new PhD program on the Berkeley campus.
Yeah.
And I'm still associated with the campus part for sure. Yeah.
So one question I had, does having a national lab so close to university allow for some collaboration with them with students?
Oh, absolutely. So there are several hundred people who have joint appointments in both UC Berkeley and LBL. I, for one, got two paychecks for like 20 years, two half paychecks. In my group and as in many of the other groups at LBL, there are many students. So in my own in my own group, it's called the Center for X-ray Optics. We always had PhD students who pursued their PhDs with us, with me as their faculty advisor. I think there were over 20 over the years who got PhDs in these related areas. And I always had undergraduate students. Also, there's a program on the Berkeley campus called Engineering Physics. It's basically it would be called applied physics in many places. But for instance, in Europe, it's more commonly called engineering physics, but it is applied physics. And I was the faculty advisor of that group for like, I don't know, decades. And it typically had 80 students at any given time, 20 per year per 4 years. And I always had some of them working in our group also. So, which wasn't unusual. That's the way we did things in Berkeley.
Yeah. So, how did UC Berkeley change, not just in academia, but in its entire culture from when you started to be a professor to today?
I don't think there's been a basic change in culture. They it's a campus that's known for innovation, for openness. It has it's rated by these rating organizations of what's the best universities in the world and what's the best departments and everything else. Every every department on the UC Berkeley campus is always in the top 10. They don't have any PhD program that's not in the top 10 nationwide. So, um, like the chemistry department is number one. Electrical engineering is always tied for number one or number two or something like that with Stanford, our close friends at Stanford. Same for physics and same for art history and literature. It's just a great, great place. It attracts great students. Number one. In fact, I could tell you a little side story, but it attracts great PhD students, and great PhD students attract great faculty to come there. It is a place to go because you can do great research, get great publications, and the students are an integral part of that in every way. So I don't really think the culture has changed. There's been some changes. Not well, the content, the interest and content of every department evolves over time, for sure. The class I teach has had the same name for 30 years, but every year it's different. And every year I start the first lecture by having the students vote on what topics they want to cover. But I don't think the basic culture has changed. Um, but anyway, it's a great place to be for both students and faculty.
Yeah. So one more question I had was, what should someone who's an undergraduate at UC Berkeley in an engineering major look out for, whether it's clubs, activities, research? What do you think that they should be involved in?
Well, so uh, for sure, they should join some clubs. Don't get stuck in your room studying all by yourself. That is not the way to success or to happiness. That's a way to stress. So you should join some clubs. One in your major. So the Society of Physics students, or the Society of Engineering Science students, or there's another club, HKN, honorary something or other society, electrical engineers, mechanical. You should join one of those clubs, maybe two, and you should join something that's just for fun. Intramural soccer, business classes. They have business that they had all these. I was walking through the campus yesterday. I think there's something like 200 of these clubs you can join. And you should find something that you just enjoy. Ballroom dancing, fencing, lots of business majors, computer related things, just fun things, hiking clubs. Students should join those because you could tend to get lost on a big campus. You don't want that to happen. You want to be socially involved, meeting with people outside your major, in your major. An important thing that we recommend at Berkeley is that in every class you're in, you should form a study group with colleagues in your class. You should do the homeworks together. I mean, let's put it this way. You should meet and talk in group of 3 or 4 or 5 people should meet and go over what's being asked in this homework problem? Do I understand it perfectly? Are my notes clear? Or was I writing notes while the professor was still talking and I missed something? So you should look at each of the homework problems together and understand it and then go do it by yourself and also prepare for exams together. So it's super important to have study groups, find a mentor if you can, find ways so that you don't get stressed. I do not recommend working through the night, all-nighters for anything. Your best performance is when you're well rested. So those would be some things I would recommend to students. And of course, you're going to work hard and that's why in fact you probably got into the university because you were working hard, so you already know that. Anyway, that's the things to do. So be part of the fabric in all senses and you'll do better.
All right then. Thank you for joining me on the podcast today.
My pleasure. It's great talking to you and congratulations. This is a great service you're providing to people. Okay, bye-bye.